Hi, this is Chris with Sanderson Test Prep, and we are going to take a look at a calc question that one of my students had the other day. So for this problem, it says let f of x equal the square root of 4x plus 5, and it asks us to use the linearization of f of x at x equals 1 to approximate f of 1.1. Then compare your approximation to the actual value and find the absolute error. Okay, so basically what linear approximation is asking us to do in calculus is we're going to use a tangent line to predict a value of a curve at a particular point. And the idea being that the closer you get to the actual point, then the closer that tangent approximation will be. So for example, if you have a curve that looks like this, which is the general shape of a square root function, like we see here, then if I draw a tangent line and, oops, that wasn't a very good one. If I draw a tangent line that touches, let's say, right here, well, you can see that maybe far away from that point of intersection, that tangent line might not be a very good approximation because you have a significant gap between the tangent line and the curved function. But as you get closer and closer to that point, if we were to zoom in, very closely, you can see that that gap gets smaller and smaller and smaller and smaller until if you're at, let's say, 1 and 1.1, the idea is that that might be a good approximation for what the value of the actual function would be at that point. So that's what we're being asked to do on this problem. And let's see how it works when we put it into practice. So the first thing is whenever they give you the point, we want to find what that intersection is, or we call it the point of tangency. So here they're saying that they want the linearization of f of x at x equals 1. So that part for the moment is simple. We're going to plug in a 1 for x into our function. So f of 1 would be square root of 4 times 1, which is 4 plus 5, which is 9, and square root of 9 is 3. So the coordinate there would be x is 1, and then y is 3. That's where that intersection is going to occur. That's where our tangent line is going to touch the curve. Now, what we want to do is whenever we're dealing with a tangent line, hopefully by now, when you're seeing this in calculus, you associate the word tangent with the word derivative. And the derivative of a function is the slope of a tangent line at a given point. So here, we're going to have to take the derivative of this function. And to do so, I usually recommend anytime you see a root, try to convert that into a fractional exponent. It's going to allow us to apply power rule or chain rule much more efficiently. So here I would simply rewrite this function as 4x plus 5 to the 1/2, and then take the derivative from there. And that'll be f prime of x is, so we do 1/2 times 4x plus 5. Using power rule, this will be to the negative 1/2. And then it's going to be times, we still have to multiply using chain rule, times the derivative of the inside, which is times 4. And if we want to clean that up a little bit, 1/2 times 4 will be 2. And to make the exponent a positive, we move it to our denominator. So it would be 2 over 4x plus 5 to the positive 1/2. And we could write that in as a root to convert it back to the same form of our original function. So your derivative would look like this. And since we're still working off of that same point, we want to find the slope at that point, meaning when x equals 1. So here this is f prime of x, and if we do f prime of 1, when we plug in a 1, we'll have 2 over the square root of 4 times 1 plus 5, and that'll be 2 over the square root of 9, which is 2/3. So that's what we need in terms of our outside information to be able to have enough to plug in to our linearization formula. And our linearization formula, hopefully we remember, but if not, I'll write that in here. That's going to be L of x and that's equal to your original function, so it'd be f of a plus your derivative times that difference, so f prime of a, and then times your x minus a value. And here we can plug in our a is going to be equal to 1, and so we would get f of 1, which is 3, and I'm just going to plug it in first. F prime of 1, which we know from up here is 2/3. And then just to go back a little bit so we can see it all in one place, f of 1 was 3, f prime of 1 is 2/3, and then we would have x minus 1 in our parentheses. So again, it's 3 plus 2/3 times x minus 1. Now, they want us to use this linearization. So we've done the linearization part. We found the linearization function, and in the original problem, if we go back, they want us to approximate f of 1.1. So we're using 1.1 as our value for x here for our approximation. So we're going to take L of 1.1, which would be 3 plus 2/3 times 1.1 minus 1. And if we do the exact math on this, this comes out to, you can use calculator for a little help, but you're going to get 3 plus 2/3 times 0.1. And so that 0.6 repeating moved over a decimal will end up giving us 3.06 repeating on that for our linear approximation. And then the second part of this is they want us to compare that to the actual value. Now the actual value is always going to be our original function. And rather than scroll back and forth on you, I'm just going to rewrite that here. But our original function was f of x equals the square root of 4x plus 5. And so to get the actual value, we're going to plug in this 1.1 that we see here into our original function. So f of 1.1 will give us the square root of 4 times 1.1 plus 5. And again, we can use a little bit of calculator assistance here, but when we do the math on that, that comes out to the square root of 9.4, which is going to be 3.0659. And then to find your absolute error, you're simply taking the absolute value of the difference in these results. So we're trying to find out how far off our approximation was from the actual value at a particular point. And so here, when we do that, our absolute value of 3.06 repeating, and just to keep the decimals the same length, I might do 3.0667 here minus 3.0659, and we would get 0.0008. So that would be our absolute error on this question. So again, with linearization, conceptually, we're just trying to find out the difference between the value of the tangent line at a particular point versus the value of the actual function, and take that difference to figure out what that error would be. And so we can see that our result here is an absolute error of 0.008 with a linear approximation of 3.06 repeating and an actual value of 3.0659 on this question. For more, please stay tuned and check out our other videos. Thanks for watching.